you are new to Topcoder, whether you enjoyed the round as such.
So I'll give it to you, misof, to share your screen, get the whiteboard on, and we can start discussing.
Yeah, sure.
We have a good number of audience here. Yep. So
Okay,
looking forward to
let's
the
see. Chromium tab. Okay. I do have a whiteboard shared. Hopefully you can see the whiteboard. So,
yeah, it's visible.
Okay, so let me talk about the problems we had in the match today. And I will start from Division 2, from the very easy ones, and then we will gradually get through all of them. So today we had 6 problems prepared. The first 4 were used in Division 2, and problems 3 to 6 were used in Division 1. So 2 of the problems were shared between both divisions. The easiest problem was about constructing TIE fighters. So this was a very easy problem to get everybody started. A TIE fighter is an ASCII art figure that looks like this. There is a central cabin, which is an uppercase O. There are 2 of these wing pylons, and there are 2 solar panel wings, which are dashes and pipes. And you are given a string with spare parts, and you have to assemble as many TIE fighters as you can. So this problem is just about counting everything. So you look at the input string you are given, and you count the number of occurrences. So how many of the pipes you have, this is X. How many of the pylons you have, this is Y. And how many cabins you have, this is Z. And now if you want to assemble a TIE fighter, then you need 2 of these, 2 of those, and 1 of the other one. So the maximum number of TIE fighters you can assemble is the minimum of 3 supplies. So you need to have enough cabins, you need to have enough wings, and you need to have enough stuff to connect the wings to the cabin. So you divide X by 2, rounding down, you divide Y by 2, rounding down, you take Z, and the minimum of these 3 quantities is the number of TIE fighters you can assemble. So this was mostly an implementation exercise to get used to the system, to get used to how you implement the class and work with strings and so on. So if you already know how to talk to your programming language and convince it to do what you want, then you should be able to get this accepted during the contest. Okay, so now problem number 2. In the second problem, what we had is a slot machine. So this is a device that is used for gambling. We have a machine. The machine is sometimes called a one-armed bandit because it has 1 arm. This is the lever you pull to operate the machine, and it's called a bandit because it steals your money. You come with money and you leave with nothing, so that's why it's called a one-armed bandit. The machine has several reels, and on each of those reels there are some pictures of fruit, and the fruit we are interested in the most is a cherry, and if we see a cherry on each of the reels, then we win the jackpot. And in this problem, we were given an information about this machine, and the machine was completely deterministic. So for each of the reels, we knew what it looks like when we stretch it out. So there was, for example, an apple, a pear, then a cherry, then again an apple, and then again maybe a banana. And there is always exactly 1 cherry on each of the reels. So we were given an information about what the reels look like. And then you were given also the information that whenever you pull the lever, each of the reels rotates by a fixed number of steps. So if this reel rotates by 7 steps, then you see the apple, and when you pull the lever, you can see some fruits passing by. You will see a pear, you will see a cherry, an apple, a banana, and then again a few of them, and after 7 steps, the reel will stop. So you can always tell from its current position what is the next one. And the question was, what is the number of times the machine has to be played until we hit the jackpot, because we want to let some other sucker play for the times it doesn't win the jackpot, and then we come and just play the ones when we get the jackpot. So what to do with a problem like this? We need to realize that everything in the future is exactly determined by the current position of each of the reels. So at the beginning, we know that each reel is rotated so that element 0 is the one that's visible, and we can keep track of this index as we pull the lever over and over again. So if I pull the lever and the first wheel rotates by 7, then the index changes from 0 to 7. Then in the next step, it will change to 14, then to 21, and so on. But of course, we are always counting modulo the length of the reel. So as we are playing the game, we can keep track of each of the reels. We can at any moment tell which of the fruits on the reel is the one currently visible on the display of the slot machine. And this collection of indices can be called the state. This is what represents exactly what the machine is currently looking like, and what we can expect in the future. So if I tell you the current state, this is how the reels are rotated, then you can simulate the machine from this point on, simulate next rounds of the game. And what this means is that as soon as one of the configurations is repeated, we know that the machine has entered into a loop. So the same configurations will then repeat over and over again. So in order to detect whether it's actually possible to win the jackpot or not, we can just simulate the process until a configuration repeats. Now the input in this case was small enough, so we can make some very rough estimates when this will happen. So what is the number of possible states? If we have a reel that has 5 possible positions, another that has 3, another that has 4, then clearly an upper bound on the number of actually reachable states is a product of the lengths of those reels. So on the first reel can be in any of 5 positions, the second one in any of 3, the third one in any of 4, and this gives us 5 times 3 times 4 possibly reachable states. So at least at most after that many steps, the machine has to enter into a loop. And we can detect this in many different ways. Just for example, we can even afford to store the entire history and for each state check whether we saw it previously or not. So we are just simulating the machine until either we detect the loop or we detect the jackpot. Detecting a loop can also be done by simulating a sufficiently large number of steps and saying that if we haven't seen a jackpot by now, if we simulated 5 times 3 times 4 steps and there hasn't been any jackpot, then we know for sure that there will never be a jackpot on this particular slot machine. Finally, the nicest way of solving this problem, what we can realize in problems like this, where the next configuration is always determined by the previous one, it always pays off to think about reversibility of this process. If I tell you the current configuration, if I tell you for the machine what it looks like at this specific moment, can you tell what it looked like one step before? And in this case, yes, you can. You just have to rotate each of the reels the correct number of steps, but in the opposite direction. So it's the case that not only the next configuration is always determined, but also the previous configuration is determined. And we start from the configuration when all of the reels are at 0. We go to the next one. From there, we go to the next one. And sooner or later, the machine will enter into a cycle. And now the main observation is that the cycle has to be entered by returning back to the original state. Why is this the case? Well, because if we enter the cycle anywhere else, if we entered it somewhere here, so the initial configuration doesn't repeat, but some other configurations repeat in a cycle, then what we would get is there will be a configuration that is reachable from 2 different configurations. And this is impossible because in this process, we have reversibility. We can always we can look a step back. So probably the nicest way to solve this problem is to simulate the machine until either you get the jackpot, or you get back to all the reals being rotated to the initial position. If the jackpot happens first, then you win. If the jackpot doesn't happen until you return to zeros, then it never can happen. So that's problem number 2. Before I move on to problem 3 and 4, just a quick reiteration that if you have any kind of questions or comments about the problems, feel free to type them into the chat and I'll try to react accordingly. So let's erase the whiteboard again and move on to problem number 3. Problem number 3 was the problem about a poisoned swamp. And in this problem, we have to cross a poisoned swamp. And it's a standard grid problem in which you are traversing a grid graph under some constraints. But I still like this particular problem because it kind of challenges your initial idea of states. If you are a beginner to problems like this one, then you may be tempted to think about states in this problem incorrectly. So let's talk about this particular problem, what it looks like. So what we are given is a grid. So the usual 2-dimensional maze you get in many other problems. There are some obstacles, which are cells you cannot enter at all. There are some cells that give you poison, and the poison is always specified by the amount of poison you will get. And there are also some cells that contain springs that will heal you to full health, remove all poison from your character. So this is something we have in this problem. And the question is whether you can or whether you cannot get from the top left to the bottom right without ever hitting 10 or more poison. So that's the problem we are trying to solve. And the statement was helpful in that it already showed you one tricky part about this problem. So what can happen in this problem are situations like this. Let me draw a very small picture. So here's a wall, there's a wall, this is a corridor that you have to pass. And there is a lot of poison here. And there is a cleansing spring here. And usually in grid problems, it doesn't make sense to return to the same cell multiple times. You can usually walk along a simple path and reach the solution that way, and this can be used to maybe give an upper bound on the length of the solution and such. But in this problem, there is no way to cross through this swamp by going by stepping on each cell exactly once, because if we want to do that, we try to go straight, we will get 12 poison and we will die. But the problem is still solvable. What you can do is you can go like this. So at this moment you have 8 poison. Then you make a detour to the spring, you clean yourself, so your poison goes back to 0. And then you go like this, and again you have 8 poison, but you survived. So what this means is that you cannot think about this problem in terms of your location only. You have to think about the entire representation of the state you are in. And this representation includes not just your location, so not just your coordinates, but also the current amount of poison you have. So instead of imagining a graph that has just R times C vertices, one for each cell, when solving this problem, you need to imagine a graph that has R times C times 11 vertices, or maybe just times 10 is enough. So you have to, in each vertex, you are at some coordinates, some row, some column, and you have some amount of poison between 0 and 9 inclusive. And now on this graph, we can make the transitions. If you make a step up, down, left, right, what happens? You move to the other coordinates, and maybe you get some poison, or maybe your poison is set to 0. And now in this new graph, in this state graph, what we are asking is whether there is any path from the initial state, you are in the top left corner with 0 poison, to any of the states, any of the vertices where you are in the bottom right corner and your poison is still less than 0. So it is a simple use of a graph traversal algorithm, depth first search, breadth first search, whatever you prefer, but you have to do it on a new graph. You have to build a graph with 10 times as many vertices. You have to keep track of the amount of poison you have as a part of your state. All right. Any questions, any comments on problems presented so far? Yeah, so far, yeah, we have several of the all-time greats with me here in chat. So far, they are just silently watching me explain stuff. But don't worry, we will get to the harder problems, and then I will question them and talk to them about their ways of solving the problem. By the way, welcome, Lewin. Haven't seen you before here, so glad you could join us at least now. Okay, let's move to the problem number 4. This was the hardest problem in Division 2 and the second problem in Division 1. The previous 3 problems were authored by me. The problem I'm going to talk about now and the hard problem in Division 1 were authored by Lauriu, who sadly cannot join us today on the stream because he has like 2 a.m. now and he has to sleep. So make sure to post words of praise to him directly or write it on some message board if you like the problems, so that he can hear it afterwards. Okay, so what this problem looks like is that we have a sequence of numbers. And we have 2 players that have kind of opposite goals. One of the players is a maximum player, the other is a minimum player. The maximum player wants to maximize the value at the end of the game. The minimum player has to minimize the value at the end of the game. But the operations they have to do alternately is kind of going against their own goal, because the maximum player has to select 2 consecutive numbers and remove the bigger one. And the minimum player has to select any 2 consecutive numbers. For example, after removing the 9, they may also select the 5 and the 2, and they always remove the smaller one out of those 2. And the 2 players have to take alternating turns until just the single value remains, and that's the outcome of the game. And we are asked a very traditional question in combinatorial game theory: assuming both players played the game optimally, what is the outcome of this game? Who will be the winner? Or more precisely, what will be the value that will actually be there at the end of the game? And this is a very nice problem, because it turns out that there is a correct solution that is like 1 or 2 lines of code, but it requires some thinking, some playing around with the problem and discovering what exactly these crazy operations can do. And one of the things we can observe is when we start playing around with this problem, as I did when I was test solving this problem. And speaking of test solving, one other person I should praise for this round is Mike, who has been a tester for this round and who has diligently solved all of the problems and helped us arrange them and polish them to prepare them for today's round. So thank you, Mike, if you're watching. So back to the problem. If we can notice when we are playing around with the problem that some interesting stuff is happening at the ends of the playing field. So if I'm, for example, the player who wants to maximize the result, and if I make my move at the very end of the playing field, what happens is that either is the situation like this. So I now have to remove the 3. And what I did with my move is that the left endpoint is now smaller than it was before, which may be something I don't like. The other option is that if the endpoint is actually smaller than the element next to it, if I select these two, erase the bigger one, the left endpoint remains the same. So I don't have any way to make the left endpoint bigger. I can only make it smaller if I touch it in an unfortunate moment. And the same is true for the right endpoint. I cannot make it bigger. I can only make it smaller if I'm clumsy and I select it in an inappropriate moment. But the same thing is true for my opponent. For these two values at the ends, they cannot make them bigger. They cannot make them smaller. They can only make them bigger. So in some sense, I don't want to touch those. My opponent doesn't want to touch those. But sooner or later, one of us will have to do it. So what matters the most is who is the last person to make a move in the round. If I'm the last person to make a move, what happens during my move is that I'm shown the very last two numbers. And if I'm, for example, without loss of generality, if I'm the one who wants to maximize the value, and I see a 3 and a 7, then I'm forced to throw away this 7 and take the 3. And if the last move is my opponent's, then my opponent will be in a similar situation. They will be shown the last two values, and they have to take the worst of those two. And from these observations, we can now formulate a theory and then think about proving the theory. And the theory is that the optimal result will be that we look at the beginning and the end of the array, as the array is given at the very beginning of the game. We look at the parity of the length, so we can calculate whose is the last move. And if the last move is the player who wants the maximum, then the output is the smaller of those two numbers. And if the last move is the player who wants to minimize the value, then the output is the bigger of those two numbers. So this is the theory. And for the proof, we actually already kind of discussed what both players have to do. So if I'm the player who has the last move, all I have to do is never to touch the two endpoints before the very last move of the game. If I do this, they can either remain the same as they are in the beginning, or my opponent can improve them from my point of view. That's the only two things that can happen. So I just make arbitrary moves in the middle of the array until the very last move of the game, when I'm forced to choose one of those two endpoint values. And so in this way, I can guarantee that my output is at least as big as the smaller of those two values. And on the other hand, if my opponent wants to make sure that I don't get anything bigger, all they have to do is also never to touch any of those endpoints. If they don't never touch them, they will never change them, and they will make sure my very last move will be exactly this last situation. So kind of a complicated process that arises from very simple rules, and we can mathematically show a very interesting solution that is simply look at the first number, the last number, the parity of length, and make just two cases, whether if n is odd, then it's a maximum, and if n is even, then it's the minimum, or vice versa. All right, so.
Are there other solutions you expected for this problem, other than the one-liner?
For this one, no. This was the only solutions we had in practice. All of us came up with the same solution.
I saw someone in my room had a binary search on the answer, I think.
I didn't find the solution, so I had a binary search solution. But,
I see.
I did a linear search, but also had the standard reduction to 0-1 problem first.
Yeah.
Yeah. If you binary search the solution, so then you can create values that are, if you are the one who wants to have big values, and you are trying to check whether you can solve the problem with output at least x, then all of the values that are x or greater are good. There are ones, and all of the values that are smaller than x are bad. There are zeros, and in this case, it no longer matters whether the value is exactly x or bigger. You can treat all of them equally. So this is the reduction to a 0-1 problem that other people are talking about. There is a question whether this can be done with the dynamic programming. The problem with this is that you have exponentially many possible states. As you can make the moves anywhere within the array, you can actually reduce it to many different versions of many different subsets of the input array. So dynamic programming can reduce the complexity only if you are doing it naively only from something like n factorial to something like 2 to the n. Andrew has a comment that, yeah, we stopped like halfway through the binary search solution, that after we reduce it to the 0-1 case, obviously we still have to figure out the solution for the 0-1 case. It's easier to argue about it in the sense that you don't have to think about minima and maxima. You just have to think about, can I get a 1 or can my opponent force me to have a 0 at the end? So in some sense it's easier. In some sense you will discover the same formula in the end. Just the analysis is simpler. All right, so I think that's probably enough about this problem. We still have 2 problems left. So problem number 5 is a scheduling problem. We have a collection of jobs. Each of the jobs has a length, and each of the jobs has a penalty, and the penalty is non-decreasing. In this particular problem, we used some cubic functions just because they are easy to describe, but the solutions are I think all solutions I've seen are kind of general in the sense that they don't need the assumption that it's a cubic function and anything non-decreasing would work. And again, this scheduling problem is kind of a little bit less traditional because of the way the penalty is calculated. So what we do in this problem is that for each job, we look at its completion time. So if we arrange them, so if this is the flow of time, and you have the 4 jobs arranged along the x-axis, that you finish job number 1 at time t1, then you finish job number 4 at time t1, so length of job 1 plus length of job 4, and so on. So for each of these jobs, you take the time when you finished it, you compute the penalty that corresponds to this time, and you don't take the sum of those penalties, which would be the usual in scheduling problems, but in our problem, you take the maximum of those penalties. And now the question is how to find the schedule that minimizes this maximum, that minimizes the overall penalty for those jobs. And this is a problem that can be approached again in multiple different ways. But I will start with a way that doesn't directly work, and it's kind of a good thing to mention that in this kind of scheduling problems, usually a very good thing you can do is think about swapping 2 consecutive jobs. If we are usually, especially if we are maximizing the sum of some kind of penalties, or we are trying to get as many jobs accepted before deadlines or whatever, then the question, what happens if I swap 2 consecutive jobs, is very useful because it doesn't influence anything that happens before. It doesn't have to influence anything that happens after. It only affects those 2 jobs, and we can think about the criteria. When does it pay off? When it doesn't pay off? And sometimes, if we are lucky, we find that this property that swapping these 2 jobs pays off is transitive, and when it's transitive, then it gives us a greedy algorithm when we can sort according to this property and get the only correct optimal order. In this case, when we are taking the maximum, it kind of breaks the pattern in that many of the swaps are completely irrelevant, and there isn't, in general, transitivity. So we had some kind of like swapping solutions that are giving incorrect answers, and there have been tests to fail these. But we can still use a very similar way of thinking about this problem. So I will now explain first a solution that finds a greedy set of criteria, how to directly construct the optimal order. And then I will mention another way this problem could have been solved. So for the first solution, Let's start with some basics. So first of all, as the penalties are non-decreasing, it then doesn't make sense to make any gaps between those jobs or to go like half of the job, then half of another job, and so on. So we are just looking for an order, one job, another job, without gaps, without anything. The only thing we are looking for is a permutation of the jobs. Now, regardless of the order in which we do them, the moment when we finish is always the same. This is the sum of the lengths of all the jobs. And one thing we can look at are the penalties for all of the jobs at this particular moment in time. For each of the jobs, we can calculate the penalty it would have if it was the last job on our schedule. So this is another of the standard patterns how to analyze problems like this. You can either start from the front or you can start from the back. Start thinking, can I tell which job I should place first into the schedule? Can I tell which one of them I should place last? So let's think about placing one of the jobs last. For each of them, I can calculate the penalty it would have. And now the claim is that if I take the job that has the minimal penalty at this particular time, I can greedily place it as the last job in my schedule. So this is something I now claim. So now I have to prove that this is correct. So let's assume that this was the schedule that had the correct job as the last one. And now we have some different schedules. So we have another job here. Then we have our job, and yeah, I think 8 might whiteboard. Then we have a collection of other jobs. And this is the job instead. So suppose somebody claims that this different solution is optimal. What can I do now? I can do this change. I can take the job with the minimum penalty at the end, and I can move it to the end. So what happens is that this job will be done sooner, this job will be done sooner, and this job will be done at the very end. So compared to the original solution, to the one pointed to by the arrow, this penalty of the leftmost job remained the same. We didn't touch it. Those jobs now have smaller or equal penalties because we shifted them to the left. And this job at the end has at most as big as a penalty as this job did at the end, because the blue job is the one with the minimum penalty at the end. So if we take the maximum of penalties here, and we take the maximum of penalties there, when we shifted the other jobs and the blue job was pushed to the bottom, the second schedule has to have a maximum that is at most as big as the first schedule. So if the first was optimal, the only option is that the second is equal and optimal as well. So this is the entire argument, and now it gives us a very straightforward quadratic time algorithm. So go through all the jobs, find the one with the minimum penalty at the end, place it at the end, forget about it, go to n-1 jobs, and so on. As an exercise, you can think about speeding up the implementation of this for more than 1,000 jobs, but this wasn't necessary, so you could get the solution in quadratic time. So this was approach number 1. And now approach number 2 is that this problem was also solvable via binary search. So another solution pattern is that if we have a hard problem where we are asked to compute the minimum or the maximum of some property, in this case, the minimum penalty that is reachable, we can think about whether the property is monotone. In this case, it is. What it means is that if there is a schedule that costs at most 1,000, then there is also a schedule that costs at most 1,001, 1,002, and so on, because it's the same schedule. So there is some specific cost of the schedule where the answer flips from yes, you can do it, to no, you cannot do it. And now we can ask the binary question. We can ask the question, for this specific limit, is it possible or not? can you get below this penalty or not? And in some cases, this doesn't help, but in this case, this is one of the many problems where this particular pattern helps. So you can find a solution like this. So suppose we already fixed some value x, and we are asking the question, is there a schedule such that the maximum penalty is at most x, it doesn't exceed x? In other words, we are simply asking the question, is there a schedule in which the individual penalties of all of the jobs are at most x? And again, this is the time axis. This is the fixed ending time, the sum of all job lengths when we have to end. And now there are two possibilities. Either all of the jobs would have a penalty at the end that is bigger than x. And if this happens, we can immediately say that there is no solution. If you have at least one of the jobs that has a penalty that is small enough, you can just greedily place it there. If you have multiple jobs, you can greedily place them in any order you like. And this is shifting the time farther to the left. This is decreasing the penalties for all of the jobs. And at any moment in time, you either have some more jobs that already have penalties low enough that you can place them, or you run out of jobs and you see that, okay, I was able to place all of these jobs, but now the penalty for all of the others is still too high and none of them can be added to the schedule. So either you successfully construct one correct schedule and know that X is possible, or you find a contradiction, find a set of those individual jobs, those that remained unplaced, and for those you can show that there is no way to arrange them to get a penalty less than X. So in this way, you could use binary search to find the optimal value of X. You are binary searching just over integers, so this is like 60 iterations, and the checking can actually be implemented even in, I think, linear time, but even if you did it in quadratic time, it should still be plenty fast. All right, contestants, questions, comments? Did you do something similar to what I described? Did you do something completely different?
Yeah, I did research. Yeah, go ahead.
Go ahead, yeah.
Okay, I mean, okay, I was doing binary search and binary search inside, yeah, and I like the quadratic solution. I mean, it's easier to implement because the binary search solution is prone to, like, the errors, like the binary search range has to be like close to the limit of 64-bit integers, right? And then
if you are using signed integers and you are not careful, you can actually get an overflow in the binary search solution.
Yes, if you do you have to do left plus difference divided by 2, for example, or to get the middle element, right? Or I used unsigned.
Using unsigned
integers, that's
safer,
fine. But yeah, I guess most of the challenges for this problem actually came from this factor.
Yeah, like briefly checked solutions, and it seems that almost nobody did the beautiful solution without binary search, but I was lucky to find one in my room. So during the challenge phase, I was first I spent 5 minutes trying to fail, and then I was very excited to see that it works.
5 minutes to admire the beauty of the solution.
Yeah, exactly.
This is one of the parts I like about the problem, that it does have this less traditional solution as well, and the reward is that it's easier to implement.
Like the quadratic solution, the best thing about the quadratic solution is that it has no constants inside the code. Like you just calculate some values by the formulas.
Yeah, Roman has a question whether there is any difference which job you use if some of them have the same penalty, and the answer is no. You can do the argument with any of them, so each of them is can be used in some optimal solutions. All right, so that was the last of my problems, and now for the second problem that was prepared for today by Lauriu. Let me open it just to refresh my memory. Hooray for the modern education. As I have been already giving some lectures online, and I already have like 2 monitors and a tablet set up so that I can draw on the whiteboard and also open some other stuff. So what we have in this problem, we are doing some kind of standard combinatorics in that we are counting permutations with some specific properties, but this particular set of properties is less traditional, I would say. I haven't seen a problem like this before, and it was kind of fun to, again, play around with the problem and discover what exactly those constraints are telling you. So what we have is a permutation of numbers 1 through n. So let's do an example permutation. Something like this. And now for a specific value of k, we can look at all possible segments of this permutation of length k. For each of these segments, we can take a look at the minimum of those elements. So the minimum of 7, 1, and 3 would be 1. The minimum of 1, 3, and 4 is 1. Here the minimum is 2, 2, and again 2. And then we can take the maximum of all of these values, which is 2, and this will be the value f of our particular case. So in this case, we had k equal 3. So the f of 3 is 2. And now somebody else had a permutation, and they did this operation, and they did it with every possible k. So they did it with k equal 1. So this is just looking at, if we have k equal 1, we are looking just at each individual element. Each individual element has its own value, and when we take the maximum of those, we will always get n. So in this case, we will get that 7 is f of 1. Then we take a look at all segments of length 2. We get the value f of 2, f of 3, and so on, all the way to f of 7, where we look at the entire array. The minimum of the entire array is 1, so 1 is always the f of n. And the problem was asking you that here are the values of f, all of them, and you have to count all of the permutations that exactly match all of these. So it kind of tells you some local information about the permutation, how long are the segments of some values, and you have to come up with a clever way of counting all of these permutations. Okay, and this will be the most interesting part for our distinguished contestants panel we have here, because I will describe the one solution we have, and then I'm kind of expecting to hear from you about maybe some slightly different approaches you could have had. So let me collect my thoughts a little bit. It's been a while since I last dealt with this particular problem, so I have to get swapped away memories of it into my head so that I don't mislead you too badly. So it should be clear that as we are going through the sequence where f1 is always n, and so on, and f of n is always 1, then the values in a valid sequence can never increase. They can only remain the same or decrease as we are going from the left to the right. And what they tell us is, so we now want to have a slightly different look at the same information we have been provided. So suppose that it tells us that f of 3 is 5, and f of 4 is only 4. What does this mean? This means that if you look at all possible segments of length 3, each of them has to contain at least one element that is 5 or bigger. But somewhere there is a range of 4 consecutive elements No, it's it's the other way around. So always when you have 4 consecutive elements, at least one of them is small. At least one of them is 1, 2, 3, or 4. But you cannot have a smaller gap with just these small numbers. If you look at the segments of length only 3, each of them has to contain at least one of the bigger values, because f3 is already greater than 4. And all right, moment of awkward silence until I compose my thoughts.
If you want, I can continue. But up to you.
Yeah. So essentially, what we I will tell the big picture idea of the solution, and then I will let you fill in the details. That would be probably the best. So the big picture idea is that imagine that we are assembling the final permutation one element at a time, and we start from one end of the elements to the other. So we are placing the elements from the biggest to the smallest into the permutation. And we have already placed some of them. And as we did so, we have created some connected components of elements. And once we did so, it no longer matters what each of these individual values are. It also doesn't matter how the components are arranged, because all of the arrangements are kind of equivalent. So we can represent the current state of the construction as some partial partition of the value of n. So these are the individual states are like partially constructed permutations, where we just need to remember the lengths of the connected blocks of values that have already been placed into the permutation. And then each time we are adding a new value, we'll check some conditions to make sure that we are only constructing valid states that are on the track to the correct solution. And remember, for each of those states, the number of ways in which it could have been reached. And the main reason why this solution can be fast enough is that stuff like integer partitions is known to grow exponentially, but the exponential growth is very slow, especially at the beginning. So if you specifically look at integer partitions of numbers, then the number 50 already still has only like around 170,000 integer partitions only. So the number of actually reachable states during such a construction is reasonably small. And now over to Petr for more details.
I think that's pretty much it. So I think the solution, I think myself and Gennady, we discussed we have solutions going from different ends, but the one that works faster, which Gennady is implemented, is yes. So if we look at the numbers from small numbers to large numbers, like where is 1, where is 2, and so on. So after you have looked at those numbers and removed all of them, the rest is split into some set of segments. And in order to verify the condition from the statement, what matters is the maximum length of the segment. So the maximum length has to be exactly some number computed based on the input of the problem. And yet then you have partitions, and for each partition you need to remove one element from it, and then the corresponding number of the partitions potentially splits into two numbers. I was going in the opposite direction from the end, kind of starting from the bigger numbers and merging the partitions. Then I have the same number of states, but I have more transitions, it seems. Or at least less efficient transitions. And therefore my solution actually had to squeeze to fit this time limit after the contest ended.
But maybe you actually have more states for some reason, because like not all of the states can be reached going from small to large. Like, for example,
yeah, that makes
from
sense.
the number of ones in the input, we know the exact first step, right? Because like from all the 50 states we can go to, well, 25, we can only keep one and so on. I guess going small to large might be more efficient for that reason. But other than that, yeah, there is not much to add. So I would say that, yeah, we go from small to large. So like, I mean, whatever. I think that whatever I say will not add much. So yeah, we go from small to large, and we want to know the maximum length of a segment, which does not contain any numbers from 1 to k for each k, basically. And then we iterate on the position of the next number, k plus 1, and it is removed from its segment, and the segment it was contained in is split into 2. And again, we want the maximum of all the segments to be exactly some number. And that's how we build up our dynamic programming.
All right.
So I like that the problem had constraints 50, because it's like the old style, you know.
Yeah, we also liked it during testing that it turns out to be a very good place, because, and also I mean, I already mentioned it, but I will go back to it again, that usually you expect that 50 is like the quintessential number telling you the solution runs in polynomial time, because like if you see 20, then you look like for something like 2 to the n. If you see 30, 35, you look something like mid in the middle, 2 to the n half on one side, 2 to the n half to the other side. And if you see 50, then you know that 2 to the 50 is already way too much, 2 to the 25 is already more than borderline too much. So probably you are looking for something polynomial. And in this case, it's not the case. It's actually worst case exponential if we were to do it for a general n, but the exponential starts very slowly, and the number of states for n equals 50 is still manageable.
I think the number of partitions function is like, might be the only thing I can think of that I've seen on Twitter where 50 gets through without a polynomial solution. I think there were, I can remember maybe at least 1 or 2 other instances where the runtime was based on number of partitions. But yeah, I don't think there was anything else that was exponential but did work for 50.
There are some meet in the middle problems, right? Sometimes.
Maybe, yeah. But then if you have n times 2 to the n over 2, that's already too much. So
some kind of pruned brute force. Like I tried to write some time ago generalization of a vertex cover problem, where if you do just the naive brute force solution correctly, then the recurrence is not so the time complexity is not 2 to the n, but it's much lower, because in one of the branches you remove a significant portion of the graph, so the time complexity recurrence is t of n is something like t of n minus 1 plus t of n minus 6 or 7 or something like that. And again, this kind of problems can lead to situations where you can solve 50 vertices graphs in under a second. But,
you said that was in one of the SRMs, or was that?
I think it was for one of the SRMs, but I don't remember the name of the problem anymore.
If you could find it, I would be curious to take a look.
Yeah. I'll try to find it and post it somewhere.
Sounds good.
All right, so let's try to use that we have all of these people here on stream willing to answer questions. And if we have people in chat that still have questions, maybe not just related to this SRM, then very quickly until all of us get bored and leave, please ask those questions and we will have our guests answer them for you. Okay, let me finish the screen share so that you are bigger. Yeah, okay, now our pretty gets in a much bigger resolution.
I'm actually curious from Lewin, what were your impressions of the round when you tested?
Oh, I didn't test this round, so I actually just competed in it. But
Oh, wait.
yeah.
Oh, okay. Sorry, I thought you were a tester.
Mike was the tester.
Got it.
Plan to keep the idea of 4 problems?
For now, it was an experiment, but let's say it was a successful experiment after today. So we may
I like this
return.
format better.
We may return to this experiment more frequently now that it looks like it worked.
I guess it depends on the difficulty of the hard problem. So today, after the first 3 problems, which I can, my solutions were not the shortest ones, but I knew that I would solve them sooner or later. I only had half an hour left for the hard problem, which sometimes might not be enough.
Yeah, in general, it may make sense at least to go from 75 to 85 or 90 minutes if we had a 4th problem. And there's a comment from God Shiva, which is precisely about what we are doing today. Division 1 easy should be doable, and 4 questions should facilitate this. That's precisely what we are trying to do. So today's 250 in Division 1 was very approachable. It was the poison swamp problem, where it's just a standard technique with a little bit of a twist if you are not so experienced. And yeah, but everybody who has been setting problems for contests knows that it very much depends on what you have available, and sometimes you have problems that go well together, sometimes you have problems that don't. Today, we had we decided to have problems that are kind of, so 3 of the 4 problems in Division 1 were on the easier half of the spectrum, just to give at least some fraction of contestants enough time to work on the 1,000, or maybe it was a good strategy to start with 1,000, that some of the people did.
Yeah, about the 4 problems, actually, several years ago, when misof only became the admin for the first time, and CGY Forever was the admin before you, I guess, right? Yeah. I actually wrote a post on the forums, on top of the forums, advocating for going to 4 problems on a regular basis, because at that time, like the way it felt like, it was pretty hard to do 3 problem contests balanced enough. Like the problem is that in Division 1, even in Division 1, we have people of very different skills, right? So we want the easy problem to be doable, solvable by almost everyone, and at the same time we want like the hard problem to be almost unsolvable, like solvable by only like a small number of people, right? And then you have the medium problem, which if half of the people solve the medium problem, which is kind of a good thing, then this medium problem is probably easy for the top people, and then they only have a contest of 1 problem.
Yeah, and on the other hand, if you have a medium problem that is very difficult, then the top is happy with having interesting problems, and most of Division 1 has a 1 problem contest where they are ranked based on the speed and on the easy one.
Yeah, exactly.
They do not,
and also challenge,
so
also challenge phase.
Yeah, also challenge phase. That's correct.
But yeah, so yeah, that's what I actually wrote, and after that, like misof started to like coordinate rounds, and I feel like he's done a great job in that, like in, I don't know, fixing this gap maybe, because after he started doing rounds, it felt like it's not that bad, and probably it's doable to do, like it's possible to do 3 problem rounds interesting for most people. But I feel like it requires much more, I don't know, fine tuning maybe to make an actual interesting round for everyone. And I feel like, I felt like at that time, and maybe I feel like that still, then that maybe 4 problem rounds are just easier to, like, I don't know, they can have a wider range of
kind of statistically, if each problem you set is a random variable that is somewhere around what you desire it to be, then if you have more problems, then more frequently you will be somewhere closer to the middle on average, and you will have fewer of those outliers. So in this sense, it's more sensible to work more problem rounds. But yeah, it's something we have to kind of play around with, tweak the parameters and so on. So we'll see what happens.
All right. Yeah, the question is, won't 4 problem rounds make it difficult to finish the last problem on time? Yeah, maybe just increase time, right? Increase time by a small amount. It's a solution to that.
Yeah, in terms of today, I thought the solve counts look quite good, where a very large majority of contestants were able to solve the 250, and then you had like fairly smooth curves to the 400 and 550, and then the 1000 looks like it had about 11 solves, which is also a pretty good number, I think.
I guess this round was still a bit on the easy side, but it's fine.
Okay, so we have a few questions from the chat, so let's go through a few of them. There was a question, how do you guys train for competitions? And also, so this was from Andri, and Philip is also asking a related question, how much time do you spend competing, practicing, creating problems? So is anybody still actively do you feel like you are actively training for competitions nowadays, or no?
No, maybe on average, I guess 1 or 2 2-hour contests per week, just competing.
Yeah,
I mean,
so
yeah, for me, I guess that just doing the competitions, the online contest, has been the way to practice for quite a long time. I guess, like, I have done the latest Petr training camp with some teammates, which was like a week ago, maybe. So, I mean, sometimes I do some training, and also like there are open cups, right? Open cups are team competitions that are 5 hours on Sundays, not every Sunday, maybe every second Sunday. So that's also some training, right? But overall, like, I would say that just doing all the competitions out there is a good training in itself. So if you have enough time to do them, then, like, I mean, it's already good. And then if you have extra time, you can do virtual participation and you can do app solving, but I usually don't do either.
Yeah, for me, I'd say pretty similar, mostly just entering contests. And then I guess in terms of training, it would be kind of the reviewing the contests you did afterward and up solving if you missed a problem. And that's amazing.
Yeah, it's pretty similar for me, but I don't do it as much, I guess. I mean, I do Open Cup like very rarely, but yeah, I still try to keep involved. Like as for like preparing problems, I try to like be involved in like the regional contests, but like a lot of those are delayed. So I think we're having like the North American one coming up in a couple of months, and I'm helping with preparing that.
I would say, as for preparing, yeah, maybe misof can comment on that. on the amount of
I
time.
do spend a bunch of time preparing problems nowadays. At any moment in time, I do have a noteboard with some notes about like, hey, this particular problem looks interesting, take a look at it. And I have like a repository of unfinished codes when I have like some Python script examining the properties of non-square divisors of whatever, whether there is a nice structure of that can be exploited to make a problem out of it and so on. So yeah, part of my brain is always set in these like problem setter mentality when I go around the day-to-day life. It's there's sometimes this like warning sign, hey, this is interesting. This may make a nice competition problem one day. Write it down, you dumb person, because if you don't write it down, you will forget about it. So yeah, I have also on my cell phone access to my notes about problems, and sometimes like at 2:30 in the morning when I look at some unrelated YouTube videos and I come with an idea, I write it down before I fall asleep, and the next day I look at the notes and say, oh, okay, I don't remember what this was, and erase it. So yeah, writing problems is a part of.
I can totally relate to the feeling of, yeah, like searching for problems constantly in the world around you. I mean, at some point of time, I was actually like trying to actively come up with problems, and basically I was thinking about it passively like all the time. And I'm not sure if that's healthy, but you know. And also another story about my problem setting is that at least once I'm sure that I came up with a problem in sleep, because I'm sure I wasn't thinking about anything about like that when I went to sleep, and then when I woke up, I had exactly like a problem idea in mind. And then
I remember several occasions when I solved something in my sleep, and then I couldn't remember the solution when I woke up, but I was certain I had it when I was in the dream.
Yeah, that has happened to me as well.
So I think one thing that I think you Neil do is you actually do streams, and it also in some way is a practice, because if you discuss problem solutions on a stream, it means you have to understand it better and maybe think about it more, or you don't see it like it's.
All right, I guess we exhausted the audience and ourselves. So thanks everybody for joining us for the stream, helping us celebrate this like 800 SRMs and 20 years of top coder matches. We are very happy of hitting these milestones. And also thanks to everybody in chat and everybody who joined us for the round. And we are happy to see you joining us, taking part, and see you for the next SRM, I guess.
Yep. Thanks everyone. Thanks for joining. Thanks for taking your time and explaining the problems and having a great chat about the other things as well. So thanks a lot.
Thanks everyone, and see you all in the future.
Well, thanks everyone. And yeah, I think I missed Peter's question, so I just wanted to say, yeah, definitely relate to what he said. I missed that he was asking me. Sorry.
Yeah, I guess Neil is the most active streamer out of all of us, right?
Yeah, I think so. Yeah, and then Peter is
like,
the most active.
He was
blogger.
actually like, yeah.
Used to be.
Blogging is also. Oh, sometimes you do still. It's okay. It's also practice, right?
Yeah.
I also have a side streaming career at the moment. I'm streaming in Slovak some quizzes approximately once a month. So I have several hundred of people following and taking part in these quizzes. It's also fun, something to do on the side to relax.
Nice. All right.
All right.
See you all. Bye-bye.
Okay, thanks.
Bye.
Thanks a lot.
Thanks everyone.
See you.
All right, Adam.
Okay. Hey, thank you, everyone. Thank you for joining SRM 800. What an amazing day. A lot of fun, a lot of great conversations. This is a special treat for us. so happy to have all of you here. What an amazing turnout. And I just want to say thank you for spending your Saturday, few hours with us, and of course, amazing job in the arena. And of course, I'm always excited to have that group of competitors together, talking, sharing their thoughts, their ideas, the problems. I mean, it's a special treat. So I hope everyone definitely appreciates all of their time and their voice in all of this and what they have to offer and to teach everyone here. So thank you. Thank you from Topcoder. Thank you from the Topcoder community team. Amazing job, Harshit. Thank you. And of course, to all of our problem writers, this was a great day. So SRM 800. Anything else, Harshit?
You concluded it well, Adam. Thanks a lot, everyone. Great day, great contest. We hope you liked the 4-problem idea, and we probably, as discussed, we want to carry it and try it a few more times and see how it works out, and then probably implement it and use it for a lot more SRM. So thanks again for joining in, for being a part of the celebration, and we hope to do this more often and bring everyone together, bring a few competitors, as Adam said, and have you guys attend and see and have them talk into the problems or talk about their journeys and get inspired from them.
Yep. I wore my retro Topcoder today, so happy 20, happy 800. So big days, big milestones, 2021. I'm looking forward to having an amazing year with all of you. So this is awesome. Thank you.
Thanks, everyone. Thanks, Adam.